Hello and welcome to this tutorial. In this tutorial we are going to discuss how offline maximum power point tracking methods are utilized or used implemented in a typical solar photovoltaic system. So first of all, let's discuss about the basis of the offline MPPT and their types. There are two types. One is known as the fractional short circuit current and the second type is the fractional open circuit voltage. The basic theme of both of these methods is the same, so we are going to discuss only this fractional short circuit current method in detail, because the same thing can be applied on the open circuit voltage method. So let us see what actually these methods are. Now if we draw a typical IV curve of a typical photovoltaic panel, where this is our current I and this is our voltage V. This point you can know this is known as the V open circuit voltage, where this point is the maximum power point. So the voltage corresponding to this will be V MPP, right? And similarly we have this point which is known as the I short circuit current, and this point is I maximum power point. So you can see that if we measure this ISC, then by multiplying this, then adjusting this difference or computing this difference or adjusting this difference in our algorithm, we can reach this point MPP. And similarly for the open circuit voltage, this VMPP actually is at a distance of a fraction K2 from this VOC. So in either case we have to measure the offline parameters. So for fractional short circuit current, we need to measure the short circuit current ISC of a PV module, and for this method we need to measure the open circuit voltage of the photovoltaic module. Now this value usually in the mathematical expression, IMPP is equal to K1 time is approximately equal to K1 time into ISC. Let us call it equation number 1, because we are going to use this equation for our rest of the lecture. And VMPP is approximately equal to K2 into VOC. So this equation number 1 principally deals with the fractional short circuit current method, and this VMPP deals with the fractional open circuit voltage method. So one thing is sure, that at any instant of irradiation and temperature, these values are quite close. The short circuit current and the maximum power point current, and the voltage at MPP and the voltage at the open circuit. So now let us see how we can adjust or how we can make our system work at fractional short circuit current. So in order to do this thing, first of all we need a panel, and here is our DC to DC converter that is used for maximum power point tracking. And let us suppose here is our load, which is not a dynamic load, it's a resistance based load. Now we have to connect our panel with the DC to DC converter, and we have to feed it with some duty ratio D. Now this duty ratio is computed here in this MPPT block, which I am implementing with the short circuit current MPPT. Now this short circuit current MPPT requires two things. First, it requires the I short circuit, and secondly it requires the photovoltaic instantaneous current. So how we can find out this ISC is, we can use a static switch here, and we have our current sensor here. Let us consider this a current sensor. So this give us IPV as well as ISC. So when at an instant when we start at the starting instant, when we need to measure the short circuit current, we will close this switch. When this switch will close, this panel will be short circuited, and during that time no power will go to the DC to DC converter. So we will store this value of ISC. Let us suppose ISC is equal to 5 ampere at a certain instant, and then we will stop this switch, because this is for just for one instant, very small time. Then what will happen, it will measure the IPV, because after that it will compute some duty cycle, and the DC to DC converter will start tracking the power and deliver it from the photovoltaic module to the load. So at that instant this will be measuring this IPV. So our algorithm is very simple. We have to measure the ISC, we measure this ISC, and then we multiply it by the factor K that we have discussed here in this equation, this K1 into ISC. So we will measure it with K, let us call it K1, and this will give us the IMPP, approximate value of IMPP. And then what we'll do is this, we will be having a plus a comparator. This will be our IPV, and this will give us to some sort of controller where we are using a PI controller, and this give us the duty ratio. So this is our simple, and remember this type of maximum power point tracking method is the most simplest method. We require only one sensor, only one current sensor is required. Or if you are having a voltage based fractional short circuit, fractional open circuit voltage based MPPT, you required only one voltage sensor. Here you required only one current sensor. Now how we can find out this K1? This K1 can be find out by some data sheet. So for example, we have a data sheet that states that IMPP is equal to 6 and I short circuit is equal to, let us suppose it is 8. So K will be equal to 6 divided by 8. It will be somewhere around let us compute it. It will be equal to 0.75. So 0.75 will be the value of this K1. So let us see how this technique works. For example, at an instant, this is the photovoltaic curve. The system will first of all isolate the photovoltaic module and measure the I short circuit. So we will be measuring this point. This value is recorded, right? So let us suppose it is 8 ampere. After this 8 ampere will be multiplied with this K1, and if we, because this K is usually from 0.75 to 0.9, for better modules it is close to 0.9. So by multiplying it will give us this MPP. So if we consider it 0.9, then we will multiply, we will compute IMPP is equal to K1 times ISC, that is equal to 8 into 0.9, and this will give us 7.2 ampere. This will give us 7.2 ampere, considering this to be 0.9. This 7.2 ampere will be checked with the IPV. So at the initial value, if this IPV is, let us suppose 7 ampere, initially we will be having an error of 0.2, which will be adjusted by this PI controller, and it gives us the required duty ratio. So but if this method is so much easy to implement, then why we don't use it so often? It is because of two reasons. First, there is no intelligence in this method. In conventional short circuit current method, there is no intelligence at all. So it cannot detect the change in weather. For example, if your panel is operating at this new photovoltaic power and voltage curve, it will never be able to know that this value has changed. So in order to cope with this thing, most of the conventional techniques works on two things. Number one is a time based measurement. So the time based measurement means that we need to measure the ISC every, let us suppose, uh, every 10 minutes. So every 10 minutes means a huge power loss. This straight away means that if we have this type of power curve for our whole day operation, we will be measuring this short circuit current every 10 minutes at a rough scale. This shows that for every 10 minutes there is a power loss, because at these instants no power is transmitted to the load, because it is you short circuit the photovoltaic module, and at that instant of short circuiting, when you short circuit this one, no power is going outside. So this is actually a power loss. In some few advanced methods, one that has been published by me, I have developed some intelligent techniques of sensorless detection of when to short circuit a photovoltaic module, but that will be discussed later on. The point is this, that it is that a time based measurement requires that we are losing power, which is unacceptable. Therefore this technique is considered not efficient technique. However, it do have some advantages. The first advantage is this: its convergence speed is very high. That is, the moment it short circuits the photovoltaic module and records this value, this D will be very close to the operating point. So at this instant, when you measure this thing, you start operating very near to this point. Let us suppose at this point, and this point is very close to maximum power point. So this convergence speed is very fast. So even if we have a dynamic weather condition, but we still have these type of power losses that are incurred because of the periodic measurement of the short circuit current, this convergence speed is very high. Third, its advantage is it's very simple. Very simple, only one sensor, which means less cost and economical, overall economical system. However, it do not operate at the true maximum power point, because it is just an approximation. We stated that IMPP is equal to K times into ISC, and this is approximately equal sign, shows that this never operates at the true maximum power point. So if you are using this thing, it is, I suggest that this type of method is a good implementation is good for those applications where we don't need very highly accurate photovoltaic systems. However, one interesting advantage of using this technique is in hybrid technique, where we speeds up our perturb and observe method. Uh, we can speed it up, and that too with the aid of this fractional short circuit current to fractional open circuit voltage. And lastly, let us have the flow chart. So you start our system here. You start it here. First of all, you measure ISC, then you multiply this ISC to find it K1 into ISC, then you will be having IMPP minus IPV. This is some sort of error, so let me write it again. So we have error is equal to IMPP minus IPV, and this goes to the PI controller for calculation of D, and that ends the system. But for the periodic tuning based system, we will be having a counter here somewhere that counts that for every 10 second, if it will count it here, that if t is equal to 10 second, then what will happen, it will again go and will measure the short circuit current. So this is how our fractional short circuit methods works. For the photovoltaic open circuit fractional method, we will be measuring the open circuit voltage and hence the voltage at maximum power point, and hence the error will be computed between the VMPP and VPV, and the rest of the method will remain same. So that's all for today. Thank you very much.